All right, this is your final exam review. There is not a PDF paper thing to study. If you want something to study and look at like that, just look at the paper PDF reviews that you got for all the other tests, because that's what it would be. This final exam has 38 problems in total. That's 34 of them as multiple choice and 4 of them where you work out the problem by typing in the solution. Total of 108 points to earn, where the last 2 questions are graded out of 5 points each. There are formulas that are given to you at the top of the exam. So you don't need to memorize them. These formulas are given to you. I do use a different formula for future value than what is given. This is exactly the same thing as e to the RK times the present value. And the one that you're given is this one. But I don't care for that formulation, even though it's true. And you're given the consumer and producer surplus formulas. Make sure you know this algebra. This is all algebra that you're supposed to know already. You might have to differentiate a square root. You would need to write it like that. This is quite often handy. The definition of the logarithm, and then some important properties of the logarithm. When it comes to limits, you know that the two-sided limit exists only whenever the one-sided limits both exist and agree with each other. Also, remember that the limit as x goes to a can be different from f of a. F of a doesn't even need to exist for the limit to exist. And the limit will only exist whenever this happens. However, if the limit as x goes to a, it agrees with what the function evaluates to at a, then f is said to be continuous at that point. It's only continuous at a point. In order to know that the function is continuous everywhere, it has to be checked at every point. And so that definition of continuity tells you that if you want to know what some limit is, just plug in the number a into the function. If you get a number back, then the function was continuous there, and that's your answer. Otherwise, you won't get a number there. You'll get some kind of indeterminate form. And if you get an indeterminate form, then you must do some algebra. So I have 2 examples to look at. In the first one, if you put in, these are the same. What I meant to say was this. In the first one, if you put in the 0 for x, you're going to get 0 over 0. So you have to do some algebra, right? This would be the limit as x goes to 0 of x times x minus 3 over x times 4 minus x. Now x is approaching 0, it doesn't equal 0, so then x over x is just a number 1. And you can cancel them. So this says the limit as x goes to 0 of x minus 3 over 4 minus x, which is just a minus 3/4. Down here, as x goes to 1, and I meant to say that I meant to have the same function down here. Come on. X squared minus 3x over 4x minus x squared. Down here, if x is going to 1, then you won't get that indeterminate form, right? It would just say 1 squared minus 3 over 4 minus 1. You get minus 2 over 3. It's continuous at 1. Speaking of cancellation, this is an important property from algebra. You can only do this whenever you have a multiplication by 1. That's it. I saw a lot of people canceling stuff when you can't. Come on. What do I mean when multiplying by 1? Well, it was whenever, so for example, x squared plus 1 over x plus 1. Let me say it like this. Sorry. Okay. Then one of these, you can cancel the x's. And in the other one, you cannot. You cannot cancel these x's. You don't have a multiplication by 1. Convince yourself that that's true. Let x be any number you like. Like maybe x is 10. Then if you could cancel the x's, then here we'll take a to be 8. Then if you could cancel the x's, then these would be the same number. And they aren't. So here you can't cancel. In the other one, you can cancel. Because an x can factor out of the top. Let me change this to x squared. Then an x can factor out of the top, and you would have 1 plus 8x. And down in the denominator, you would have another x. That can be reinterpreted as x over x times 1 plus 8x. Do you see me multiplying by 1 right here? Of course. So those x's will cancel. Okay. So unlike those formulas that are given to you at the top of the test, you must know these derivative rules by heart, right? The derivative of e to the x is itself. It's the unique function with that property. The derivative of the natural log is 1 over x. If you have anything that looks like x to some power, where this number n can be any real number, then the derivative is the well-known n times x to the power of n minus 1. This is a statement of the product rule. It's the derivative of the first times the second plus derivative of the second times the first. This is different from the sum of two functions f and g. This is the product of two functions f and g. This is the sum. For the sum of functions, it's easy. You just differentiate term by term. And then over here we have the constant rule. If I want to differentiate a function and it looks like a constant times this other thing, then I just need to find the derivative of the other thing and multiply by the constant. This is important. This is the definition. Don't get confused about the difference between the definition and the interpretation of the derivative. If you are asked for the definition or to use the definition, make this statement in the white letters, because that's the definition. It's the limit of the difference quotient. Make all of this writing right here if you're asked for the definition. Alternately, it's perfectly valid to have this other formulation, which I actually prefer. Why do I prefer it? Because look, this part right here, you recognize that. That's the slope of the secant line between w and z. So if I just take the limit as w goes to z of the slope of the secant line, I get the slope of the tangent line, which is one of the interpretations of the derivative. The interpretation of the derivative evaluated at a point is either the slope of the tangent line at that point or the instantaneous rate of change of the function at that point. Both of them are valid interpretations. The equation of a line, in case you don't remember, I'm sure you remember. Everyone on the, people who didn't even take algebra might know that this is the equation. No, probably not those people. Look, anybody who ever took algebra remembers y equal mx plus b. Don't try and make it harder than that. That's the equation of a line. Now, together with that knowledge and the fact that the slope of the secant line is just this, then we see that the tangent line would be this limit, but hey, that's f prime of z by definition. The tangent line at this particular point is the derivative evaluated at that x value. Then, when you are asked to find the equation of the tangent line at a particular point, like z comma f of z, then follow these steps and you will have it. I want you to literally write y equal mx plus b. Then you just need to find m and you need to find b. So the next thing you do would be to calculate the derivative and evaluate it at z. That will be what your slope is. I want you to go back to what you literally wrote down, and if you did it with a pencil, then get your eraser out and erase the m and put in that number, f prime of z, because you're going to have a number, and you write it down. Instead of m, you put whatever number you got for f prime of z. Then you back up to the point where you are going to be tangent. That point is z comma f of z. Both of those are numbers. And it has the form of x comma y. So use those values x comma y right here and here. M is a number you just found. Then this is the difference of two numbers, which is equal to b, the last thing you were trying to find. This is what y is. This is what m is. And this is the x value in question. Now that you have found m and b, you have your line. So in the end, this y equal mx plus b is just this. And the underlying stuff is numbers. The x and the y, you leave them as x and y. The chain rule. The chain rule is a product of two derivatives, number 1 and number 2. You know that you have a situation where you must use the chain rule when you have a composition of functions. All you have to do is view that function that's on the inside of the f. So f is like the outer function because look, it's on the outside, and then g is like the inner function because look, it's on the inside. Then view that outer function f as being evaluated at just a symbol. Just a symbol. Like this star. And observe that that symbol star is this other function g of x, but we don't need to know that right now. In order to find the derivative of this here composition of functions, I would have to compute the derivative of f. I would have to compute the derivative of g. They are then multiplied together. But I'm not going to evaluate them at x. I'm not going to evaluate them both at x. F gets evaluated at star, f prime gets evaluated at star, and g prime gets evaluated at x. Now, the derivative of e to the star is just e to the star. And the derivative of g is just g prime, but star was g prime. So you get this other, not other, so you get this. You get this, you get what happens, look, like this is a special case, not a special case. For a little while they did this as a separate rule. We don't need it as a separate rule. We have the chain rule. The separate rule was if you have the derivative of e to some function, it was e to that function times the derivative of that function. Likewise, you once upon a time had a special rule for the derivative of the natural log of a function, but it ain't that special because you got the chain rule. The outer function is the natural log and the inner function is the star. Then the derivative of this composition of functions is the multiplication of the derivative of natural log times the derivative of g. And the star is just g of x. So you get this. And we used to say that this was a special case of the derivative of natural log. You also know this as the relative rate of change. Notice I haven't said the quotient rule is something that you need to know. You do need to know it, but maybe it's hard to remember. I like to make sure that we all know that the quotient rule is a special case of just the product rule together with the chain rule. It's easy to see. Look, here I have a quotient of two functions. But using that property from that special algebra property that we're supposed to know, then that g of x in the denominator can be written with an exponent of -1 and being multiplied by the numerator. Then it becomes a product rule. So the derivative of that rational expression, f over g, would be the derivative of the first times the second, and then it's plus derivative of the second times the first. Well, here's the times the first, and all of this is the derivative of the second, because you would use the chain rule. The outer function looks like something to the -1 power. The derivative of a something to the -1 power is of -1 times that something to the -2. And what is that something? It's g of x. So I have to multiply by g prime of x. There it is. In the next step, I rewrote the g of x to the -1 like this. That is the same thing as g of x to the -1 if you combined it. Because this one has an exponent of 1, and when you add the exponents, -2 plus 1, you just get -1. Then the g of x to the -2 can factor out, and this thing written down here at the bottom is the quotient rule. This g of x to the -2 would just be written in the denominator with a positive exponent of 2. The marginal functions just mean to take the derivative of the function. Easy. So, like if you had a cost function, then the marginal cost is the derivative of the cost function. You should keep in mind that revenue is just the number of units times the price per unit. But the price per unit does not have to be the same all the time. The price per unit might change as the number of units sold changes. And if that happens, then the price is a function of x. If so, then the marginal revenue which is just r prime, would be the derivative of this product, which would be the derivative of the first, which is 1, times the second. Well, there's my times the second. And then it'd be plus the derivative of the second times the first. So that's marginal revenue. However, if the price is always fixed at the same price all the time, no matter what, then your marginal revenue, R prime, would just be the derivative of X times P, but P is a constant, it's always the same. So you would just get P. And that makes total sense to you because the marginal revenue is like the revenue on the next item sold. And if the price is always the same, then it makes sense that our revenue on the next one sold is the price that we charged. The profit, remember, is revenue minus cost. You could write it like this, revenue minus cost. So the marginal profit, you would just differentiate term by term. It's R prime minus C prime. And if your profit function, then if your price is a function of X, then you would get this. Else, if your price is fixed, then you would just get, if your price is fixed, then you would just have the marginal profit as the price minus the marginal cost. The average functions, average cost, average revenue, average profit, you divide by X. So then, average cost, C of X over X. Average revenue is the price. Average profit, average profit is just this because the profit is right here. And if I divide by X, I'm just going to get P minus the average cost. The price minus the average cost. However, I want you to remember, please note, the marginal average of whatever function, marginal average cost or whatever, you have to think about it. Marginal means derivative, average means divide by X. What do they want the margins of? They want the margins of the average function. So that means we should take a derivative of the average function. So the margin, so then the marginal average cost, let's say they want the marginal average cost, you would take the derivative of this. Don't confuse this with something like the average marginal cost, which would first have us take the derivative of the function and then divide by X. So in other words, this is different from the derivative of the function divided by X. If you are asked about shape of the graph, then you just need to follow some basic steps. This stuff should be make pretty good sense to you of why you would do it. So if I want to know about the shape of f, then I'm going to have to talk about f prime. Since f prime is going to tell me if f is decreasing or if f is increasing. You can do this with one of those number line drawings, provided that you have identified the critical values. And of course, if f of x is 0, then you have a horizontal tangent line. You do not know if you have a local minimum or a maximum if all you know is f of x is 0. It does not have to be the case that you have a local min or a local max when f of x is 0. Take, for example, if you had the function x cubed. It just goes like that. And it has a horizontal tangent line at 0, but no local maximum. Okay, let's find all the intervals where this thing is increasing and decreasing. So f prime is 4x cubed minus 8x. Now that factors like 4x times x squared minus 2. And it factors even further as 4x times x minus root 2 and x plus root 2. Then I can see that my critical values are 0, root 2, and negative root 2. I make my number line drawing with all those values. I grab the very easiest test point that I can find, which would be 1. I take the 1, I put it into f prime, the derivative. F prime of 1, all I care about is if it's positive or negative. I don't care about what the number actually is. F prime of 1 is going to be negative because it would say 4 minus 8. So I'm going to be decreasing in this interval. Now, since all of these factors are unique, then this thing just alternates back and forth. If any of these factors are repeated, then you won't have that alternation, and you'll need to use the test point method in each interval. So then I am decreasing from negative infinity up to minus root 2, and from 0 to root 2. And I am increasing on all the other intervals from minus root 2 to 0 and root 2 to infinity. If you want to talk about local extremes, then you need for your critical value to be zero. You need for your derivative to be zero at the critical value, and that it has to change from increasing to decreasing, or that it changes from, I said that backwards. It has to change from increasing, decreasing, or decreasing to increasing. Then you get one of the local extrema. Concavity. That has to do with the second derivative. To determine the concavity, you take the second derivative and you see where it's zero or undefined. Then these values of C are just the critical values of f prime. Again, you make your number line drawing. You use test points in each interval to see if it's either positive or negative. If you get negative, it's concave down. If you get positive, it's concave up. What is concave up or down? F is concave up or down. It says P, it should say C. It's actually going to be concave up or down everywhere in that. Sorry, it's not C. It is P. So I have to fix this. This is not right. So if f prime of C, C being a critical value of the derivative f prime, you make a number line drawing with each of those critical values. You use test points, and it's those test points which are these little p's. And you check in each interval to see whether the second derivative evaluated at the test point is positive or negative. F double prime of C won't be either. It'll be either zero or undefined, because that's what F double prime of C does. To be a point of inflection, you need several things. Number one, you need this point to be in the domain of your function. Number two, you need the f double prime to come out to be zero. Can't be undefined, has to be zero. And f has to change concavity at this point. If you get all three of those things to happen, then this point is an inflection point. So it's like it's concave up, and then it's concave down. But just because I switch concavity does not mean necessarily that I had an inflection point there. Look at this graph. concave up, it's concave down. This is the graph of 1 over x. But 0 comma f of 0 is not an inflection point because 0 isn't in the domain of f. And you also wouldn't have the second derivative of 0 equal to 0. It'd be undefined. For local extrema, you can also use this other, more elegant method where you have to know that the tangent line goes horizontal. So here's my function. This is f. I have to know that the tangent line goes horizontal right here at C. And I also have to have that it changes from decreasing to increasing or it either changes from, sorry, I'm screwing up. That's the old methodology. If I have this here critical value where not just any critical value, but the ones where the tangent line goes horizontal, then if I check that critical value, in the second derivative, then here I'm getting concave up and here I'm getting concave down. So if we can determine the concavity at the places where the tangent line goes horizontal, then you can know if it's a local minimum or a local maximum. For an absolute extreme, you are usually dealing with a closed and bounded interval. And if so, then your function absolutely will have a minimum and a maximum. It's guaranteed. All you need to know about are the places where the tangent line goes horizontal, and you only really care about the places where that happens on your interval. Then you just compare the numbers. The biggest one is the absolute extreme, and the smallest one is your absolute minimum. To see why you would always have a extreme value on a closed bounded interval, then here's some function, but this is A and this is B, and then right there would be a critical value. Then it's like I'm limiting my function's domain. It's like I'm limiting my function's domain to be somewhere in here. And as you can see, one of those dots is higher than all the rest, and one of those dots is lower than all the rest. Right? Because, whoops. That's f of C, and this is f of A, and this is f of B, and f of B is my absolute max, and f of C is my absolute minimum. Elasticity of demand. You would be given a demand function that tells you for a given price how many units are demanded, And if so, then the elasticity of the demand, I like this formulation. But hey, that's the same thing as the typical formulation. This is the elasticity of demand. You are sure to see it several times, or need it several times. Minus P times the relative rate of change of the demand function. If there is some particular point such that when you stick it into the elasticity of demand function, you get 1, then revenue is maximized when the price is set to that value. How would you get the demand function, how would you get the elasticity of demand function equal to 1? You would solve this expression. This just says the numerator is the same as the denominator. That's what it means to be 1. Demand is inelastic if the elasticity is between 0 and 1. That would be a product like gas. Even when the price of gas goes up to $5, it doesn't mean you stop buying gas. It just means you pay more. You know, the trucking company doesn't shut down, and just because the price of diesel goes up, they just have to buy it and pass along the cost. Gas is inelastic. Something that would be elastic might be, I don't know, cable. If anybody even still has cable. If they tripled the price of cable, quite a few people would just cancel it. The demand would go down. Riemann sums. Keep in mind the notation. This means a left Riemann sum of n many rectangles. So right Riemann sum of n many rectangles. This is delta x. The triangle means change. The change. It's the change in the x direction, which in a Riemann sum is the width of the rectangles. And this b minus a over n is delta x, because b minus a is the distance between a and b. Here's a, here's b, then this distance is b minus a. Try it. If b was 8 and a was 5, then you already know that that distance is 3, because you can count from 5 to 8, but you could also compute it as 8 minus 5. When you're doing Riemann sums, keep this little handy thing in mind. If I have a line and I carve it up into n many spaces, then I'm going to have one more of the little endpoints than I have spaces. Here's a diagram. Here I have 4 spaces. 1, 2, 3, 4 spaces. You make 4 spaces, then you're going to have 5 endpoints. It's because each endpoint, the first endpoint goes with the first space, and the second endpoint goes with the second space, and third endpoint with the third space, and so on. And when you get to the last space, there's still one more endpoint. Why is that important? Why would I want you to note that? Well, because the left Riemann sum starts with the leftmost endpoint and then just has 4 heights. 1, 2, 3, 4. All the widths of the rectangles are the same, so it can factor out. But it will have 4 heights because it's just 4 rectangles, but it starts with the leftmost one. For a right Riemann sum, you do not start with the leftmost one. You end with the rightmost one. And as soon as you realize that this happens, you can start making Riemann sums without ever having a picture or anything. Properties of the integral. This is the most basic one. You integrate a derivative, you get the function plus a constant. A constant times a function. The integral of a constant times a function is the constant times the integral. You can integrate term by term. You can break up a definite integral into multiple pieces, provided that you broke it up at some point that was between your limits of integration. For your integration rules, you don't have very many. You have these 3 rules and you don't have any other ones. So there's not a lot to remember. If I'm going to integrate something that looks like x to the n, all I need to know how to do is how to add 1. If I can take whatever n is and add 1, then I can find the antiderivative. Now that will work so long as n is not -1. If n is -1, you're in this situation. And the antiderivative is the natural log of the absolute value of x, because the derivative of the natural log of the absolute value of x plus c is just well, I mean, it's 1 over x, so you get back here. And that was what property? That was this one. And for this guy here, you can demonstrate that that's true in the same way by taking the derivative of this side. If you take the derivative of that side, then you just get e to the g of x, because e to the g of x needs the chain rule. The derivative of e to the g of x is g prime of x times e to the g of x. If you take that, so if I took the derivative of the thing in the green box, then the g primes would cancel, and you just have e to the g of x. If you don't have one of these 3 cases, then you have to make a substitution until it looks like one of these 3 cases. And that's just the way it is for, at this stage. of calculus. Here's a typical type of substitution. You have a function, and that function has factors like this. Like maybe my function is some other function of x to a power, and then it's times this other part which has the derivative of that function u. The only stipulations here are that k is some constant and your exponent is not 0 or -1. If that happens, then the integral of that function would just look like this. Look, here I just wrote exactly what's here. And then that dx is the same thing as this dx. But k is a constant, so it can come out front, and the dx's, and the dx's can cancel. I could go like this. Here I just put them on top of each other so you can see it's a multiplication by 1. Then I would be integrating that constant times the integral of u to the n. Super easy. Here's an example. Here we would take our u to be this part, right? My n here is 5, and my u is x to the 4th plus 1. So then this thing is u to the n. And the derivative of that u with respect to x is 4x cubed. So then x cubed, it turns out, is just a constant times the derivative of u. My constant here would be 1/4. Then my original integral can be rewritten as the integral of that constant times the derivative of u times u to the n. The dx's cancel, and now I'm just looking at that constant times the integral of u to the n. And since I can add 1 to 5, then I can find the antiderivative of u to the 5. And then we get our final answer. A special case. This is the case where our n was -1. So if your function looks like a quotient of two functions where the one on top is the derivative, where the numerator is a constant times the derivative of the thing in the bottom, then it will always integrate like this by substitution. The substitution would be u is g of x, and then du dx would have been k times g prime of x then here it is all substituted. And you get the thing in the box. You can also see that that has to be true, because if I took the derivative of the thing in the box, then it would be a constant times the derivative of the natural log of a function, which is the constant times the relative rate of change of that function. For example, here I've let u be the thing in the denominator. Then the derivative of that denominator is here. So the constant times this constant 1/4 times the derivative of u is my numerator. Then my original function is this constant times the derivative. This part right here is x cubed. And this part here is 1 over x to the 4th plus 1. And they are multiplied. But the dx's cancel, and the constant comes out front, and then you're just integrating 1 over u du, which definitely integrates to 1/4 natural log absolute value of u. And when you put u back in, when you back substitute with interchanging the u for what it was in terms of x, you get this. Which is exactly what we said we would get. The function looked like this. So it was that constant times the natural log of the absolute value of the denominator. Constant, 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 natural log, absolute value of the denominator. Another substitution that is possible is if you had a composition of functions. So here we have k as a constant, but u is some function of x. And with u being a function of x, look, right here I have a composition of functions. Here's my constant. Here's a constant times a composition of functions. And that's what f looks like. So then my integral of f, since f is all of this, then right there is f. The dx is canceled, and the constant comes out front, and you're just integrating that composition, but it's no longer viewed as a composition where u is a function of x, because you are integrating now with respect to u. So then for you, this looks just like a regular, that looks just like integrating a regular function, because the variable of integration is u. You just need the antiderivative of g. For example, here we have what? This is f. All of this is f. And it can be rewritten. Okay, so you have a composition of functions right here. Then that inner function is what we'll call u. So then this thing looks like an e to the u. That's a composition of functions. And the derivative of u is this 3 to the x squared, but that's just a constant times the derivative of u. And that constant times the derivative of u is part of f. It's right here. So this part of f is nothing more than this constant times this derivative. And then it's times some g of u. This right here was g of u because u was x cubed. But the dx's cancel and the constant comes out front, and now you're just integrating e to the u du. And you would just get 5/3 e to the u, but u is x cubed. Fundamental theorem of calculus is the most important theorem in calculus. It says, if I know an antiderivative of little f, then I can evaluate a definite integral of f by simply taking the difference of those limits of integration and evaluating it in that antiderivative. Don't get messed up, it's the top limit minus the bottom limit. So it's the f of b minus capital F of a. Net area. Net area. Even as early as this semester, I would confuse myself on what they meant by net area. And here's a way that I figured out how to remember it. Just like your net pay from your paycheck is after taxes, so some of the money is deducted, then the net area of a function and the x-axis on an interval may be less than the total area. This will happen if your function crosses the x-axis. So, for example, here's a function f of x that is not crossing the x-axis on a to b. So the net area and the total area are the same. Where if I just straight away integrate, this is always net area. However, if my function crosses the x-axis, like this one crosses here at z, then the integral from a to b is going to be the net area. It won't be the same as the total area. It'll be less than the total area because some of it got deducted. Right? The integral from a to b would be this region minus this region. If I wanted the total area, I would have to break it up into two integrals. I'd have to break it up at z. And I'd have to find what this positive area is and add it to this positive area. But since f is below the x-axis on a to z, then the integral from a to z will be less than 0. It'll be negative. Consequently, if I just multiply that integral by a negative, then I'm going to get that positive area. So then I can take the area of the region above the x-axis and then minus the region below the x-axis, and I'll get the total area. And that total area is bigger than the net area because the function crossed the x-axis inside of the region of integration. If I want to talk about the area under two curves, that was, it's the region that's under both curves. And it's on some interval a to b. And naturally, it's going to be trivial to be under both curves if they don't intersect. Here's one curve and then here's the other one. There's my x-axis. Here's A and here's B. Then this region's under both of them. So I would just integrate this lower function. So this only becomes tricky if they intersect. If they intersect, this is what that means, to intersect. They have the same y value for some given x value, where that particular value is in our region of integration. It's easy. All you need to do is make your first integral so that it uses the curve that's on the bottom, and then add it to the second integral where it uses the curve that's on the bottom. And that's the shaded area that you see. If the area is enclosed by two curves, then you need to follow all these steps. You would have to put the two curves equal to each other. This literally says to you that you want to know which values of x have the same, give the same y value. F of x is a y value and g of x is a y value. And if I force them to be equal, then it will pop out which x values cause that to happen. And to figure that out, you need to put it equal to 0 by moving the g of x to the other side and factor. Then you can solve it for x. So in my picture here, I have the intersection points at A, B, and C. Okay. You always want to integrate the top function minus the bottom function. Why would you do that? Because that's what's going to form a rectangle in here of that height. It would be this value minus this value gives you that height. So on just the interval from A to B, you pick a test point that's between A and B. And in this case, we would have seen that F was above G. And then on the other interval, you'd pick a test point and you'd see that G is above F. But let's note that the function F minus G is the same thing as the negative of the function G minus F. So in the region from A to B, I'm going to integrate F minus G. And in the function from B to C, I'm going to integrate G minus F because G is on top. But G minus F is the same thing as a minus F minus G, is what I'm trying to say. I guess down here for this note, I could have observed that this is the same thing as G minus F being the negative of F minus G. So what you want to do to find this yellow shaded area is you would integrate from a to b of the new function f minus g, and the other integral you would normally add the other integral of the function g minus f, but since g minus f is a negative f minus g, then you may just subtract the integral of f minus g. It gives you the same thing, because this right here is exactly the integral from b to c of g minus f. And there's our shaded area. The Gini index. I don't know if you noticed yet, but that Gini index, if it has the f of x part of this thing called the Lorentz curve, it's usually just some x to some power, like, I don't know, x to the 3.6. That's just x to some power. So I guess we'll say n greater than 0. Then whenever that happens, actually it should be n greater than 1, sorry. Then whenever that happens, your Gini index would look like this. It would have this as its antiderivative, and since you're putting in a 1 and a 0, you always just get this. You always just get this. If you distributed the 2, then you'd get this other thing. And when you finally simplify it, you'd have that as your answer. So maybe my f of x is, what did I say earlier, x to the 3.6. Then at this stage here, I'd have 2 times 1/2 minus 1 over 4.6. And when I got to this other stage down here at the bottom, it would be 4.6 minus 1, or excuse me, I screwed up. It would be 3.6 minus 1 because my n is 3.6. So my answer would have been 2.6 over 4.6. Whatever number that is. Now, if your f of x was not looking like this, then it won't work. You know, you won't be able to just jump straight to these. You'll need to perform the integration. All right, and that's it. Sorry for taking an hour and 12 minutes, but that is a complete overview of the whole semester and the final. Good luck to you.